Inverse functions are essentially functions that reverse the process of another function. And typically, because the inverse of an inverse is the original function, the reason one function is called the inverse and the other function is given a name like sine and inverse sine is that one function feels more natural or straightforward and the other one feels a little less natural. The simple example being x squared is easy to calculate, but root x is really, really hard to calculate. This means that certain processes that we do with regular functions like sine x or x squared become a bit harder or potentially more complicated when we're trying to apply the processes to the inverse, which is why we need special tricks. So we're going to look first at what happens when we differentiate an inverse function, and then we're going to focus particularly on inverse trig functions and explore integrating and differentiating when we've got inverse trig involved. So to start with, the trick here is to say to ourselves, well, we find it easier to work with the function itself rather than the inverse. So if we were differentiating inverse sine of x or arc sine of x, the first thing to do, if we have y equals arc sine x, is to apply the function sine and get x equals sine y. Then we can work with the function we know and worry about converting it back afterwards. This essentially sidesteps the problem, lets us work with the original function sine, and then we just have to find a way to rearrange things at the end. Now we've got a couple of options here, but one option, since we want dy by dx, is just to differentiate both sides with respect to x. But because we don't have y equals anymore, we're going to need to use implicit differentiation. So essentially chain rule. The derivative of sine of something is always cos of that something multiplied by the derivative of the something. So if we're differentiating with respect to x, then the derivative of y with respect to x is dy by dx. So sine y becomes cos y dy by dx. And on the right hand side, the derivative of x with respect to x is just 1. It's worth noticing that you can also do this by deciding to differentiate both sides with respect to y. So on the right hand side, you would get dx by dy, and on the left hand side, you just get cos y. Of course, you can rearrange either one from this point on, so it doesn't really make much difference which one you've done. Either way, you're going to want dy by dx as the subject. So do whatever rearranging is necessary and you'll end up with 1 over cos y. This next step here is the clever part. We have 1 over the square root of 1 minus sine squared y. It might feel like a really unnatural thing to do, but there's a very good reason for it. If we want to rewrite our derivative in terms of x so that we can actually get a sensible result for the derivative of arc sine x in terms of x, then we're going to need to get rid of the cos y and ideally replace it with something that we can connect directly to x. Now, since sine y equals x, if we can write dy by dx in terms of sine y, then we can swap out sine y for x. And there is a connection between cos y and sine y. The best one, the most direct one we can use, is the one that exploits the fact that cos squared y adds sine squared y equals 1. So cos y is the square root of cos squared y, and cos squared y is 1 minus sine squared y. And then we can swap out sine y for x, and we end up with a function exclusively in terms of x. This must be the derivative of arc sine x. Feels a little strange, but even if it doesn't look anything like trig, you can see hiding inside it the structure that dictates how the trigonometric functions relate to each other. We can see where it comes from by looking at the previous line. Cos y is the same as the square root of 1 minus sine of y squared. Therefore, we have the square root of 1 minus x squared appearing in our expression. Now you have a go. Try to follow the same kind of process and find the derivative of arc tan x. Pause the video, give it a try, and then come back and unpause to compare your result to mine. So the first step would be to write y equals arc tan x and then flip things around to get tan y equals x. Then either differentiate both sides with respect to y and then flip things over, or differentiate both sides implicitly if necessary with respect to x, and we'll end up with sec squared y dy by dx. Remember, this particular result is provided in the formula book in case you don't remember it. Now it's tempting to rearrange and write this as dy by dx equals cos squared y, but then you're likely to get a bit stuck. So try to remember that the focus of this next rearranging step is to find something that we can swap out for x. which means we need it in terms of tan y, ideally. Sec squared y is closer to tan y than cos squared y, because there's an identity connecting tan squared and sec squared together. So I'm actually going to write it as 1 over sec squared y. And then I can replace sec squared y with 1 plus tan squared y. And of course, tan squared y is just x squared. So the result comes out as 1 over 1 plus x squared. Somewhat nicer looking result than the other one, and that is related to the fact that the derivative of tan produces sec squared y, which connects more directly to tan squared. Now we have some results for the derivatives of inverse trig functions. We need to learn to look out for those particular algebraic expressions in the context of integration. In particular, if you recognize that this one is asking you to integrate something which you already know is the derivative of arc sine x, well, you could just write down arc sine x plus c, and you're done. If you need to prove it, there's a couple of ways to do that. Probably the best way is to recognize what the answer should be and differentiate it and show that it works. But you can also get there almost as quickly using a substitution. You might recognize seeing a substitution like this from A-level Maths. The trick here is that instead of trying to make a substitution for a particular awkward part of the integral, we're trying to exploit the structure of the integral. Because of the square root and the 1 minus something squared, this looks like it might have something to do with trig. So it's worth exploring and seeing what happens. The first step is, of course, to find a connection between dx and du. And although normally we have u in terms of x, and then we differentiate to get du by dx, here it doesn't really make a difference that we have x in terms of u. We're just going to differentiate with respect to u. Or you could differentiate implicitly if you preferred and rearranged. But this is convenient enough. I need dx in terms of u anyway, so dx equals cos u du. Plug it all into the integral. Replace x with sine u, replace dx with cos u du, and we get this monstrosity. Except it's not actually the monstrosity it appears. When you finish simplifying and cancelling down, it ends up looking really nice. The square root of 1 minus sine squared u is just the square root of cos squared u, which is cos u, and cos u over cos u is 1. I can integrate 1 with respect to u really easily. Just gives me u plus c. And then the final step would be, well, if x equals sine u, u must equal arc sine of x, the inverse sine x function. Now, I'd like you to try this one, but I would like you specifically to have a go at using a different substitution. There's no particularly special reason why sine should work but cos shouldn't. So even though you can see that this integral is just 4 times the previous one, I want you to try it with a different substitution and see what happens when you apply x equals cos u. Pause, give it a try, and then come back. Okay, so if we start with x equals cos u, we can differentiate as before. We can get something to replace dx by as before. There's a minus sign in there this time, but we can still swap things out. The denominator still tidies itself up because the square root of 1 minus cos squared u is the square root of sine squared u, which is sine u, so that cancels with the sine u on the top, but we're left with a minus 4. That integrates to give minus 4u plus c, and because x is cos u, u is arc cos of x. And so we've ended up, instead of 4 lots of arc sine, we've got minus 4 lots of arc cos, which might seem a little bit strange. Turns out, it really makes no difference. If you're worried about whether you should be using sine or cos for a substitution in an integral like this, they're both valid, but they might give you different looking results. Now, you might be aware that arc sine and arc cos are not just the negatives of each other. However, they are related to each other sufficiently that the integral will show us results that are offset by just a fixed amount, a constant of integration. In particular, if you have a look at the graphs on the left, I've got the standard inverse sine and inverse cos graphs drawn on there. You can see a symmetry involved. And if you flip over the inverse cos graph, then suddenly you end up with graphs that differ only by a constant. If you add pi by 2 to the inverse cos graph with a minus sign in front of it, then you're just going to get the inverse sine graph. They're not the same, but they differ only by a constant. And that constant is taken into account by the fact that your plus c and my plus c might be different. If you're starting to get worried that there's going to be a bunch of different random results to learn, then don't worry, the formula book has got you covered here. If you turn to the Further Maths section of the formula book, you'll be able to apply results directly from the differentiation section or from the integration section slightly further along. For now, we're only really focusing on these. If you look carefully, you'll see some other functions there that look very suspiciously similar to the trig functions we're used to, but they've got an h involved. So sine with an h at the end or cos with an h at the end. Those are called the hyperbolic trig functions, and you'll cover those properly when you look at hyperbolic functions. But you'll notice that a lot of the time the structures are going to be similar. So we will review and revisit this page of integration differentiation results when we look at that chapter. In the meantime, we've just got a couple of main formats to be aware of. The arc sine and arc cos results come out looking very similar, just with a minus sign instead of a plus sign. And the arc tan result is the one that looks fundamentally different. If you look across at the integration side of this, you'll see they've generalized a little bit. So they've got an a squared instead of a 1, and that makes it a little bit easier in a lot of situations to use this standard results table. Instead of hoping it's a 1 plus x squared, we can adapt for slightly different results. But you'll notice, although there's 3 results given in differentiation, there's only 2 results for integration. And that's because if you throw a minus sign onto the top of that fraction for arc sine, you could just put a minus sign in front of the arc sine and everything would work fine. You don't have to use inverse cos because you could always use inverse sine. So it's kind of redundant to require multiple different ways. But absolutely, you could represent this using inverse sine or inverse cos. If you get one rather than the other, it doesn't necessarily mean you've made a mistake. While the formula book results are useful, they give a nice sanitized version. You're unlikely to get exactly 1 over the square root of 1 minus x squared for an integral, and you're unlikely to get exactly arc sine x for a derivative. So let's have a quick practice. What would you do to exploit chain rule in order to differentiate arc cos of 3x? Pause and give it a try, and try to then simplify and rearrange your result until you end up with something in the form a over the square root of b minus x squared. Okay, if we start with y equals arc cos of 3x, differentiating arc cos, we can just follow the standard result. The only difference being, because of chain rule, instead of just writing out the standard result, we also have to multiply by the derivative of the function inside. So instead of 1 over the square root of something, I'm going to have 3 over the square root of something. It's arc cos rather than arc sine, so don't forget the negative sign that goes in front. And then in order to write it in the form that I've asked you for here, we're going to need to get a little bit more creative. In particular, we need to sort out the 3x that's been squared. And you might expand that out straight away and notice that you get 9x squared. But since we only want 1x squared, we need to find some way of pulling that 9 out. Now, one clever way to do this is to extract it from the entire square root. And if you do that, you've got to remember that you are only ever allowed to multiply by a number if you also divide by it, or vice versa. So if you have 1 minus 9x squared, you could rewrite it as a 9th minus x squared as long as you pulled out a factor of 9. Now the factor of 9 you've pulled out needs to also be pulled out of the square root, which turns it into a factor of 3. Think of it like in a binomial expansion, where you've got something raised to the power of a half. If you want to pull out a factor of 9 from the bracket, when you apply the power of a half to that 9, it turns into a 3. But once you've done that, the 3 cancels with the 3 on top. So you end up with a minus 1 instead of a minus 3 on the top of your fraction. So the value of a is negative 1, and the value of b turns out to be a 9th. It's a 3rd squared minus x squared. The reason I made you go through these hoops and try to rearrange it into this form is that if you're integrating, you're going to need it to look more like this. It needs to have a single x squared so that you can more easily exploit the standard results in the integration section. So we'll start out with a simple one that's already in a convenient format for you. Use the standard results to integrate 1 over 16 plus x squared. Pause, give it a try for yourselves, and then come back. Okay, well, hopefully this one's fairly easy to interpret. We can identify the appropriate result. It's going to be the arc tan. And then we can figure out what a must be. Since I've got 16 and they have a squared must be 16, so a is 4. And the result says I need 1 over a times arctan of x over a. So far, so good. What happens, though, if we don't have a 1 in front of the x squared? In this example, for instance, we have 1 over 1 plus 4x squared, which is not the format that the formula book provides. We need to find some way to get rid of that 4. And you've got a couple of options, but if you want to pause and give this one a try for yourselves, try that first and then come back. All right, the way I like to think of this one is scaling the fraction. So I might divide the top and the bottom of the entire fraction by 4, and that will tidy up the 4x squared, turn it into just x squared. Alternatively, you could think of taking out a factor of 4 from the denominator and get 4 lots of a quarter plus x squared on the bottom of your fraction. But then a 4 on the bottom of the fraction could be pulled out completely and called a quarter of 1 over a quarter plus x squared. However you choose to do it, it's going to end up looking like something resembling one of these. And then it's also worth replacing the quarter with a half squared. Even if it was a third, I'd replace it with 1 over root 3 squared so that I could more easily pull out for myself and extract the value of a. As soon as I know what a is, in this case a half, I can apply the standard result from the formula book. And of course, there's just a little bit more simplifying required here, and we've got the result, a half arctan 2x. If you wanted to, you could try differentiating this to prove that it went back to 1 over 1 plus 4x squared, but you might find that you've got a bit more rearranging and simplifying to do, or it might be that it turns itself into the format that we've got written there straight away. But it's usually a little bit quicker to differentiate than it was to integrate in the first place, even when the integration is pretty quick because you've got a standard result. It's worth noting that if you're asked to prove this result, that's different to just exploiting the standard results in the formula book. But you could make this work just by making sure the thing that's being squared is tan u. So 1 over 1 plus 2x in a bracket squared could be turned into 1 over 1 plus tan squared u. And because the derivative of tan u is sec squared, it's going to sort itself out. So give that a try if you like, see how that substitution works. Next up, we've got a couple of different integrals. You've got a range of methods at your disposal, including but not limited to the inverse trig that we've just looked at. So pause the video and have a go at these two to see if you can apply the results from the formula book, and then come back, unpause, and follow along, see if your method was as efficient as mine. Take a look at this first one first. 1 over 1 minus x squared. Well, it turns out this one is not an inverse trig question at all. It's not 1 over 1 plus x squared, otherwise it would be arctan. You might have spotted it in the formula book, but if you didn't, or if you thought I can do this without the formula book, probably the method you will have fallen on is partial fractions. It works really well. You can split it apart because the denominator factorizes. That's not the case with 1 plus x squared on the bottom, because 1 plus x squared doesn't have any real roots, it won't have any factors, but this one does. So we can pull it apart, we can find the values of a and b. As soon as we've got those, we can go back and rewrite the expression, the 1 over 1 minus x squared. I'm going to pull out the half as well to make my fractions look a bit nicer. And then I just need to integrate that. I'll keep the half completely outside, and then the integral of 1 over 1 plus x is ln of mod 1 plus x. For the next bit, I like to change the sign of the numerator in order to have the numerator be the exact derivative of the denominator. But that means I have to subtract the fraction, so I'm taking away ln of mod 1 minus x. You could also change the sign and call it minus 1 over x minus 1, and that's fine. Because of the modulus, whether it's a 1 minus x or an x minus 1 doesn't really make a difference. However you've done it, you can combine those two and end up with a single logarithm, which is a little more convenient. And if you look at the formula book, you'll find they have basically this same thing. Don't worry about the artanch that's kicking around at the back there. We'll get to that when we look at hyperbolic functions and inverse hyperbolic functions. It's an interesting alternative, and it's interesting that just by changing a 1 plus x squared to a 1 minus x squared, we go from inverse tan to inverse hyperbolic tan, but it's something we'll look at later on. For now, we can always make use of the log result, which will come about because of partial fractions. You might want to explore partial fractions with an a squared instead of a 1 and see if you can prove this result from the formula book for yourselves. For the second question, x over the square root of 1 minus x squared. This one does look more like inverse trig. So maybe you would try to find it in the formula book and then fail because an x on the top makes a difference. You might have decided to use integration by parts because you could split it into x multiplied by 1 over root 1 minus x squared, and that should work, I think. But I went straight for the kill with substitution because I know that that type of substitution will, at the very least, tidy up the denominator for me. And if I use x equals cos u, I can differentiate to find a way of getting rid of the dx. I can sub in cos u in place of x, and yeah, part of it cancels out, but not all of it this time, all apart from cos u. So I end up with an integral which evaluates to minus sine u plus c. Now, if you're thinking, oh, fair enough, I've got x equals cos u, the integral is minus sine u, I need to tidy that up. You might be thinking minus sine of inverse cos of x, but that's a little bit clunky. We'd be better off if we can find a more direct connection, just like with parametric equations, or in fact, with what we've been doing here, using that square root of 1 minus something squared. So if I do 1 minus x squared, I'll be doing 1 minus cos squared u, which is sine squared u, and the square root of that is sine u. So rearrange a little bit further, you'll get a result that's reasonably pleasant and involves only square roots. At this point, you might be thinking, why did I use a trig substitution? And then eventually all the trig cancelled out and disappeared, and I was back to something that didn't require trig at all. In fact, I've gone from something where I've got 1 minus x squared to the minus half to something that has 1 minus x squared to the half. And you could try differentiating and you would never need to see a sniff of trigonometry because it all just works. Bit of chain rule, it all tidies itself up, which might make you think, was there an easier way? And if you found this easier way straight away, then well done. The trick here is not to get flustered or confused by the similarity to inverse trig, just to recognize that the derivative of 1 minus x squared already appears in the integral somewhere. So if you use a straightforward substitution for 1 minus x squared, the x that's on the top of the fraction actually helps because it's going to cancel out with the 2x that we get when we differentiate 1 minus x squared. So we put that in, we replace dx, we swap out all the dx with minus 1 over 2x du. Before we worry about anything else, we do the straightforward things. We replace 1 minus x squared with u, and we replace dx with minus 1 over 2x du. And at that point, we find that the x cancels out. There was no need to try to rearrange and get x in terms of u because x disappears. Then we have something exclusively in terms of u, and we can integrate as usual. We're left with minus the square root of u, which of course was 1 minus x squared. So it gives us exactly the same result, but I think a little bit more nicely and more quickly because we didn't have to resort to trigonometry or inverse trig. Next up, I recommend a little bit of practice, both with differentiating when you have inverse trig functions and integrating when you might need inverse trig functions. Sometimes it's obvious, like in questions 4 and 8 down here, you'll see that they say give your answer in the form A arctan bx, or it's going to involve arctan, but it'll also involve ln. So you can see sometimes you can get a feel for how this is going to work. Question 8 in particular, the hint is split the fraction into 2 separate integrals. Can you create one integral that will involve arctan and another one that could be dealt with using just logs? In question 2, there's some product rule, there's some quotient rule, and at one point there's going to be some opportunity for some chain rule in question 7, I think, because after you've differentiated arc sine once, you're going to have to differentiate it a second time. So you'll end up differentiating something that's probably best written in terms of a binomial with a power. So have a go at these questions and check your answers in the book or on Solution Bank. But then if you'd like some bonus challenge questions, carry on watching the last 5 minutes or so of this video. Here's a couple of challenge questions to try. Complex partial fractions and a poor man's normal distribution. The complex partial fractions builds on the idea of the integral we saw earlier with 1 over 1 minus x squared, where the natural approach was to use partial fractions. In this case, we have 1 plus x squared, so we can't possibly factorize it, except we can if we're allowed complex numbers. So give that a try and see if you can create a complex number result by using partial fractions. And then on the right hand side, the poor man's normal distribution. If you were to sketch y equals 1 over 1 plus x squared, this is what you get. It's not quite the same shape as a normal distribution curve. It has some slightly different properties, but it has a lot of similarities. It's got the symmetry, it's got two inflection points either side, and it has the property that it approaches asymptotically the x-axis as x gets very large or very small. It's got that same sort of behavior that we've come to expect. So it's possible that we could integrate between minus infinity and plus infinity and see if it's got a sensible finite convergent value. So we're thinking improper integrals for that bit. Give these a try, and then if you want to come back and watch the last little bit, I'll talk through how I solve these problems. So for the first one, because x squared plus 1 is the difference of two squares, provided the numbers we're squaring are imaginary, we get x plus I and x minus I. We can use the same sort of techniques for partial fractions. The only difference here is that we'll need to substitute in imaginary numbers. X equals I will eliminate the first bracket, x equals minus I will eliminate the second bracket. So we can find values of a and b, and they happen to involve imaginary numbers. So far so confusing, but still it's working, so let's try it. I'm going to take out a factor of 1 over 2i to make my life a little bit easier, but then what I'm left with is just some logs. So I can apply the log result, and out pops this, which, in case you're curious, is completely equivalent to the arctan result that we would have got if we jumped straight to that using trig. So it's a little convoluted perhaps, but it's a way of connecting inverse tan directly to logarithms. And this connection, logarithms and inverse tan, might remind you of the connection between exponentials and trigonometry from when we were dealing with de Moivre's theorem and complex numbers. The second challenge question involves an improper integral. It's a little bit of a strange one because it's an improper integral that has undefined limits both top and bottom. And the official way to deal with these is to break them apart. We can't do an integral, say, between minus k and k, and then just make k bigger and bigger, because it's possible that either one or other side of this is undefined. And it's a little bit weird. It feels like maybe it would be a sensible way to do it, but it's not always going to work. So we have to first split this into two pieces. However, what we can do is make use of symmetry here and say the integral is just going to be two lots of the integral from 0 to infinity. So we'll start at a sensible, well-defined point, 0, and we'll approach infinity. But because we can't just do this with infinity, we have to sneak up on it. We'll make it the integral from 0 to k, and then we'll gradually make k increase. I can keep 2 outside the whole thing. If the integral has a limit, then the integral I care about is going to be two lots of the limit of the integral without the 2. And now it's just inverse tan. If I substitute k and 0 into that, I can start to get a feel for what happens as k approaches infinity. Inverse tan of 0 is 0, and inverse tan of k, if k is a very large number, you can try it on a calculator, you can try sketching the inverse tan graph, it is actually approaching a fixed limit. And that's because when you do tan of a number very, very close to pi by 2, but not quite as high as pi by 2, you get a really, really, really large number. If you do inverse tan of a number, no matter how large, it'll always give you an answer that's smaller than pi by 2. So inverse tan of k is approaching pi by 2 as k approaches infinity. And it turns out the area under this curve is pi. The total area of both sides, because we took into account the doubling at the very beginning, is pi. It's one of the weirder curves with an area of pi. The unit circle is probably a more logical one if you're trying to find a shape with an area of pi, but this one works too. The wonders of inverse tan.